I actually tried recording this just a few minutes ago, and my little pen that I write with did some haywire things. So hopefully this one will go better, and if I can just somehow survive it, we'll make it work. I have a split screen I'm going to share for you so that we can go through some of this together, and it just didn't seem to want to work when I had it all on the same screen. So hopefully this will do a little bit better. And you can see what's coming up in the little slides, and then we can do some writing over on the whiteboard. We're going to talk about Venn diagrams. So first of all, I guess I can make this nice and big. Our first one is the Venn diagram where the two sets have nothing in common. A and B have no common elements. The second one, everything in A is inside of B. Maybe like that kitchen drawer that has forks inside of the kitchen drawer that also includes other things. Or maybe we have just some overlap, like down here on the bottom left, which is just a very common one. So like maybe it's the things you own is set A, and then set B is the things that require electricity, and then the part in the middle is those things that you own that require electricity. Okay, but it could be that we just have the same set, and maybe we're using two different names to talk about it. Okay, and that would be our upper right one. Now in all of these, what we see is this U in that corner, and the little note down here just says U is the universal set of all elements. Okay, it's just referring to everything. We certainly are not going to write everything down, but that just kind of helps us out. So now, practicing here, this is the roster method. So if we were going to use the roster method, what would we need to do to name these? And this is where I'm going to try to go into the split screen and see if it will let me write off here to the side. And again, this is where I had some real challenges when I started trying this just a minute ago. All right. So question A over on the left here says, identify the set using the roster method. So I look in circle A, and I see items A, B, C, and D. Now, that's not quite right as written, because the roster method, when we were dealing with the set, you were supposed to put these wavy brackets around it, and if I'm not really exaggerated on my wavy, the pen tries to correct them. Now for part B, then what is the set of elements that are in set B but not in set A? So I need to look, okay, I do need them to be in B, but I don't want them to be in A. So I don't want to include that overlap. I only want this element, which is E. And again, I'm trying to make these brackets. And if I have any trouble on making it, it overcorrects it for me. But that one's set E. Now, some of you might think, well, why are the Roman numerals there? Well, I had to choose a Venn diagram from somewhere that kind of actually a real pain to draw. So I chose a Venn diagram from somewhere that I could use as this example. So it's got some elements on it that we don't quite need. So what's the set of elements that are in the universal set, which means they're anywhere on there, but are not in A? Well, if it's not in A, I need everything that's not inside circle A. So I'm going to go over here to my set notation. Not in A means I'm not going to use that circle. So I do want E, but that's not all. I also need to get F and G. And it would have been nice if I had remembered and put E first, but I didn't, and it's still a correct listing of the sets, although it's a bit unusual. So there is that answer. Now the set of elements in U that are not in A or B, so I can't go inside of either circle. So that is just elements F and G. So now the roster method is when you make a listing of everything that applies. And so that's how the roster method would apply to that problem. So I need the next slide. So here's our next one, the complement of the set. Complement. Now you might notice this complement is spelled with an E there, like the word complete. okay? So when we look at the complement of a set, what you're actually looking at is the rest of it, what it would take to complete it, to bring this set up to everything. So really, it's the stuff that is not in A, okay? Not in it. And so we have a set builder notation. That little apostrophe there that you see right after the A, that apostrophe is essentially read as complement. So this means the complement of A is the set of all X. That straight line is such that X is an element of the universal set and X is not an element or not a member of A. So I do need something that's in U, but that's not in A. If it will let me draw, if I want it to be in U, then this is my list of choices, but I don't want it to be in A. So 1, 3, 5, and 7. 1, 3, 5, and 7 are not numbers I can use. This seems to be working. So A complement is 2, 4, 6, 8, and 9. Had to use things that were in U but not in A, and that is A complement. In other words, A and A complement together would make that universal set. Anytime you put a set with its complement, it equals the universal set. So if we're going to find the intersections on these, which, let me read this through again, it's set builder. This is A intersects with B is the set of all X such that X is an element of A and X is an element of B. So it has to be in both of them. So what is it that's in both of them? I see that there is an 8 in both of those. There's also a 10 in both of them. But 6 is only in the right, 12 is only in the right, 7, 9, 11 are only in the left. So that intersection would be the set 8, 10. So that's my intersection. Now let's do it again with this next one. We've got to start over. 1, 3, 5, 7, and 9, 2, 4. This one has nothing in common. So that intersection has nothing in it, which is really the empty set. So the empty set is written like a 0 with a slash through it, which is different than a 0, okay? The number 0 can be an element, but the empty set is absolutely nothingness. Now, what do these have in common? By definition, this one, this empty set is in all sets. So it's like everything has a little bit of nothing in it. So if I want to know what's in this set that is also in the set, it's still going to be the empty set. Union means that we put sets together. So this one should have that U in it. And it means that we are going to combine them. They can be in either set. They can be in A or B as long as they're there. So if we're going to find the union, and this one is retyped, it's a lot clearer to read, we have to put all of this together. And that's where we hope I can write well enough. So I've got 6. 7 is in the first one. 8 is in both of them. 9 is in the first one. 10 is in both. 11 is in the first. And 12 is in the second. So if they're in any of them, we want them. So let's do that again a couple more times. If I put these together, and I'm trying to do these from smallest to greatest. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So you can see a lot of times it kind of can be a pain to write everything out in the roster method, and sometimes we want to use another method. Now if I put these together, we do put everything together, But all I have to do is write the braces themselves, and I've really already written the empty set. So if I want to put this other stuff in it, you can no longer see the empty set because it's a nothing that's added to a something. So that puts our sets together. So we've got union. So intersection has to be in both of them. The union is what is in them together. So now here we have this same question we actually had earlier, but this time instead of using the roster method, we're going to write this stuff with symbols, okay? So if we needed symbols somehow to do this, set A is everything that's listed in 1, unioned with everything that's in 2, and if you look up there you see those sections outlined. Or I could possibly say set A is the intersection of the universal set intersected with set A. Elements in B that are not in A, that is section 3. Section 3 right here. So here's just another way I could have said that one. The complement of A is everything not in A. And then I can intersect that with B. And this means it has to be in B because that's part of the intersection. But it can't be in A because that's what the complements means. Okay, and so that refers to section 3. Now, the set of elements that are in U, so in the universe, but they're not in A. If they are in the universe but not in A, that means I'm really wanting this section 3 and section 4 well, I guess I should have written a union there, not an and. I need 3 to be unioned with 4, but there's probably another way to say it that refers to the original stuff, and this can be kind of weird, I know, but I do want this and I do want that. I just don't want A, which really means if I want 3 and 4 and I just don't want A, I want A's complement. A's complement is just what is not in A. So what are the elements of U that are not in A or B? Well, I'm really somehow trying to name just section 4 then. So how could I name section 4 using my other sets? I could say, okay, where does the universe intersect with what is not in A and B? I could put A and B together, and then I can put this little dash out here, which means not in A and B. So if you put A and B together and then put that, that means it's not in A or B, and that would be the exact same thing as just FG. In all honesty, you really don't even need to mention the universe intersecting with it because it's all considered to intersect with the universe. So this is simply the rest of everything. If you put A and B together, once you put that the little apostrophe there, then it's what's not in A and B. Again, set A really could have just been as simple as saying set A. So now let's apply that when we're not looking at the diagram. Find the complement of A unioned with B. So this, what part A means here, is put A and B together and then tell me everything that's not in them. Okay? So I'm just going to kind of write that under here. Not in A and B. Well, together. So first of all, you put A and B together, and then it's not in that. So I do not want 1, 3, 7, 9, 8, and 10. And there's missing that little asterisk there in it. So I don't want 1, 3, 7, 9, 3 I've already marked, 7 I've already marked. I don't want 8, and I don't want 10. So what is not in those together? That's going to be 2, 4, 5, and 6. A complement intersected with B complement. Well, A complement, I'm just going to kind of write the word out here. A complement is everything that is not in A. So 1, 3, 7, and 9. So that means A complement is 2, 4, 5, 6, 8, and 10. Now, B complement is everything that is not in B. So we'll do the same sort of work again and say, okay, well, I don't want what's in B, so I don't want 3, 7, 8, or 10. So B complement then is 1, 2, 4, 5, 6, and 9. So now if I want their intersection, it needs to be in both of them, okay? So now I want to think, well, what is in both of them? I see a 2. Oh, I was supposed to pick up a highlight. A 2 is in both of them. 4, 5, and 6. Nothing else is the same in both of them, so it's not going to be in their intersection. So our final answer for this one then will be 2, 4, 5, and 6. Those are the ones that are in what's not in A and what's not in B. So now we move here, and this is actually the last slide of this particular section, 2.3, and it talks about cardinal numbers of the union of two finite sets. Well, if you're looking at cardinality, you're not looking at what the listing is, but how many things are in it. How many things are in two sets when you put them together? You need to be careful because you can't just add the number of things in each set because those sets may overlap. So you have to take the number of things in set A plus the number of items in set B, and then subtract the number of items that were in both of them because otherwise you've accidentally counted them twice. Now this is a little tip kind of down here. A lot of times it's helpful to just identify what was in the intersection, okay? Sometimes the diagram helps, but we can apply the formula anyway. So reading through this word problem, which actually came from the homework assignment, although you'll have different numbers in it, you've got a problem like this. Some of the results of the campus blood drive survey indicated that 490 students were willing to donate blood. 340 were willing to help serve a free breakfast to blood donors, and 120 students were willing to donate blood and serve breakfast. Since they were willing to donate blood and serve breakfast there, this section right there is the intersection. Okay? So how many students were willing to donate blood or serve breakfast? Okay, or has to do with they're in the first one or the second one. So I'm going to call donating blood A, serving breakfast B. So 120 were willing to do both of it. So 120 is A unioned with B's cardinality. Now, 490 were willing to donate blood. Blood was my set A. 340 were willing to help serve breakfast, so that is my set B. So, or the cardinality of it. So if you look at our formula up there, the number of the union is what I'm trying to find. How many, so that's the number, how many were willing to donate blood or serve breakfast? That will equal the number that were willing to donate blood plus the number that were willing to serve breakfast minus the number that were willing to do both, because that 120 students is in both of those numbers, okay? And then you really are ready to calculate. And I get 710.